Hello, everybody, and thank you for joining us for the June 13th edition of the Data Architectural Virtual Group. My name is Kenny Neal, and we're happy to have Kendra Little with us today to talk about how index keys and included columns work. I'm the co-leader of this chapter along with Rob Canzaneri. Let me take a step back there. You can see our contact information right there. We're both on Twitter, and if you want to get in touch with Rob, it's rob@sqltigers.com. Some look at our upcoming sessions. We've got Mark Vanderwaal actually coming back next week to talk about feeding a multi-purpose data lake. And then you can see we've got Tim from SQL Skills and Rob Sewell in September. So we've got a couple of good ones lined up for you. We have two wonderful speakers. The first is Nutanix. They've been with us for a long time now, so check them out. And then second, our newest sponsor who we're happy to have is HVR Software. Please give them a visit and thank them for sponsoring the group. They make this possible. Registration is open for the 2018 PASS Summit. You can save $150 if you register using our code right there. And then I think if we get enough people to use our code, we'll be able to give away a summit registration to a lucky person. Some upcoming virtual group webinars. Business Analytics is actually meeting tomorrow, and then you can see there are a few more there. Fundamentals, Business Intelligence, a lot of good stuff there. Some upcoming SQL Saturdays, Houston on June 23rd, and then this one wasn't originally on the list, but as my personal request, we've got Baton Rouge on August 11th. I'm actually going to push the button to make our schedule go live tonight, so I hope if you can, you'll join us for that. And with that, that's all I've got for today. So I'm going to hand it over to Kendra. Thank you all for joining us.
Thank you so much, Kenny. All right, so let me go ahead and get my screen share going. I think that I have properly unmuted myself. I see audio levels going there. So I will go ahead and get started. Welcome to how index keys and included columns work. I am Kendra Little from SQLWorkbooks.com. And at SQL Workbooks, I've got all sorts of materials that let you learn SQL Server by solving problems. I have a bunch of free quizzes you can do, and I send out a free quiz letter every week you can sign up for to get a quiz in your inbox on a variety of SQL Server topics from T-SQL to indexes. And I just think they are tons of fun. So if you'd like to get those quizzes, you can do that. And you can also download the demo code for today. Here I have the URL for where you can get the demo code that I'm going to show you today. We will also have a quick quiz at the end of this session, just on screen here, nothing too fancy. I promise the quiz won't be too hard. It's just a 3-question quiz, because today what we're going to do is we're going to explore disk-based row store indexes in SQL Server. These classic indexes in SQL Server that we can create to help make queries faster. What we're going to look at is we're going to look at how are these indexes structured. We can see using many undocumented but helpful commands in SQL Server, we can see how these indexes are laid out and how SQL Server puts different information at different levels of the index that support seeks as well as scans. We'll look at keys versus included columns. How are they stored differently? We may have already heard information about how they're stored, but we can actually see this using these undocumented tools, which I think is really cool. And we can see how SQL Server uses them. I think it's tons of fun. Now, I'm going to advance the slide. If you miss the URL for the demo code, it's going to show again at the end, so don't worry too much about it. You will have a chance to download the demo code at the end of this as well. We will be looking at a non-clustered index in SQL Server as we explore this. With non-clustered indexes, you must specify at least one key column. This will determine how the index is ordered. You can specify more than one key column. You have the option of specifying included columns on a non-clustered index, and we'll explore, okay, what is different between keys and includes as we look at this example. Clustered indexes are different. When you define clustered disk-based row store indexes. And I'm saying all these words, disk-based row store indexes, because we now have column store indexes and in-memory indexes. What we're focusing on here is what I think of as our bread and butter indexes, or our classic indexes that we use a lot of the time in SQL Server. The other index types of indexes are good too. They especially shine with certain use cases, but disk-based row store indexes, for many purposes, they are excellent still, even though we have these specialized indexes for certain circumstances. Now, for a clustered index, for a clustered disk-based row store index, it is the table itself. And for a clustered index, we specify one or more key columns on it for this type of disk-based row store index. We don't have the option to specify included columns, however, and that makes sense because it's the table itself. When we create a clustered index, we don't go create a clustered index and then, over here and the data is over there. No, when we create a clustered index, we are ordering the data itself by the key column or columns that we specify. So there's no such thing as an included column for a clustered index because it is the table itself. We specify the keys and then all the other columns are included, if you will, by default. They are still in the table. They are going to be ordered by those clustered index key or key columns that we specify. Let's take a look at the index structure. We're going to spend a bit of time in demo looking at these indexes. And I think that looking at an index and how it is structured is really, I think it's interesting and fun, but I also think that when it comes to designing indexes, it gives you a sense of, okay, what does this index look like, which helps you understand how is it going to be used, how should I design indexes for my queries. So although we're getting a little internalsy here, I really find this information to be useful for designing indexes. The first thing I'm going to do is restore the sample database I'm using. I am using the Contoso Data Warehouse database, which is a free download from Microsoft. We've had this database around for a while. I think it's a really fun, useful database. It's totally free to download from Microsoft. The demo script that I have, I'm going to restore it to my SQL Server instance. I actually already have restored it. It took 3 seconds. You may just want to change the locations where your backup file is and where you restore the data file and the log file to, depending on the disk structure you have on your SQL Server instance. I am going to configure Query Store just in case it comes in handy. We aren't really going to spend time looking at Query Store, but I am running my demo on SQL Server 2017. And sometimes I just find it handy to be like, oh, what query plan was I having? It can be, I've gotten into the habit, Query Store is so useful, of just configuring it after I restore a database because it may come in handy depending on what you end up becoming interested in as you explore it. We're going to use the database, and we will be looking at an index that we're going to create on the DIM employee table, which sounds like our employees are not very smart, but instead this is a dimension table that contains employee data. So the DIM employees of Contoso, I'm sure they're very bright indeed. This is a pretty wide table, as you can see. We have a lot of columns in this table for the employees at Contoso Retail Data Warehouse. It's only 293 rows. This is not a huge table. If you've got questions as we go, by the way, feel free to throw them into the Q&A box. I will look at them as we go and see if I can work in answers. Some questions, if we're not going to cover it for a while, I may hold it or catch up at the end. So as soon as a question pops into your mind, feel free to throw it into the GoToWebinar Q&A box. Now, the DEM employee table, by default, it doesn't have a lot of index action happening on it already. We only have one index on this, and I'm using the built-in SP help index procedure here. This thing is not perfect. It's kind of retro, not in the best way. It doesn't tell us a ton about indexes. Now, for our purposes right now, it does tell me there's only one index on the table, and it is a clustered primary key. So we have a clustered index on the table that is the table itself. The clustering key is employee key. SP help index doesn't tell us, are there included columns, are there filters, but those are not relevant to the clustered primary key. So in this case, it doesn't matter, but we're starting with a table that just has the clustered index on it. So let's create a non-clustered index for us to explore. I am going to create an index with a big old anti-pattern in it. This is a small table. And what I've done here is a ginormous anti-pattern of saying only fill up the pages in the leaf of this index 1%. What I want is to force SQL Server to create kind of a big index tree so that we can look at how the data is laid out on the root page and some intermediate pages and these very empty leaf pages in the index, because I've said only put a little data on these pages and leave the rest empty. That's going to bloat this index up to way more pages than it would need otherwise. I'm doing that on purpose just for the purpose of demo. And yes, I do know of at least one real world case where someone thought fill factor was the opposite of what it is, and it can be confusing. In their defense, it can be confusing because in maintenance plans, you specify how much to leave empty. In the T-SQL, you specify how much to put full. This is in the T-SQL 1% full. I do know of at least one case where someone put really low fill factor on all their tables and their database was bloated up. All of their space and memory was empty. Performance went way down after that. So you got to be careful and make sure you know, am I specifying how much is full or how much is empty? We are creating this as empty, and we'll be able to see that when we look deep into these pages. I'm going to check out now my index structure for this index. I'm looking at a good old friend, sys.dmdb index physical stats. This dynamic management view came to us in SQL Server 2005, and it allows us to see how many pages are in this index. We can figure out from that how big is it in megabytes, because each of these pages for a disk-based row store index is 8 kilobytes. We can do a little math and figure out the size. We can see how much logical fragmentation is going on. And over here, what we're looking at is the average page space used in percent. How much of the pages are full and how much are empty space? Now, I used 1% fill factor, so we would expect a lot of empty space on this. I am running this in detailed mode for the index with this name who I just created there. For the index that I just created, here is what index physical stats sees. We have 3 levels to our index tree. And we have 3 levels because I said leave a lot of space empty. This is average page space used. And in the leaf of our index, what's called the leaf of the index is the index, it's going to have all of the data on it. It's going to be the largest level of the index. Unless our data is, if our data is small enough that it could fit on one page, SQL Server will do that, right? But I've said fill these pages in the leaf, which is level 0, fill them 1% full. And what I actually got was 1.3% full. So I got a little more full because it's like, well, I have to put at least 1 row on each page. Come on. So I got close to what I asked for. It's not hardly fragmented. I just created this. These pages are not out of order with one another. And my leaf of the index takes up 1.9 megabytes. There are 244 pages in the leaf of the index. There is an intermediate set of pages as well. Right above the leaf, we have 2 pages that point to all of the pages in the leaf. And we're going to look at these pages in detail. These intermediate pages map to the pages in the leaf. And then there is, at level 2, we have a root page in the index. Your indexes can have different amounts of levels. As we're going to see later, if we make this index more compact, if we don't need to have 204, if we don't say fill factor equals 1, forcing there to be 244 pages in the leaf, we might not have index level 1 with 2 pages at all. That might be the root page of the index. So our index depth can differ a lot depending on how many pages do we have in the leaf and how full have we made them also. So I have forced this to be a 3-level index by saying leave a ton of empty space on the pages in the leaf. And that empty space on these 8K pages is on disk, it's in memory, it's everywhere. but it's only a 2 meg index. So my crime is very small, right? My crime is, and it's a test instance. This is a victimless crime for the sake of science. I can also see the page numbers, the identifiers of these pages for my index. We're going to use a newer friend now, and this is an undocumented friend. We're going to look at the DMDB database page allocations dynamic management view that was introduced in SQL Server 2012. This is technically undocumented. I believe Microsoft still hasn't said they support this. It replaces or provides an alternative to an older undocumented feature called DBCC end. And both of these are ways I can say, okay, what are the actual page numbers of the pages being used in this case, this index, because I'm joining to sys.indexes and saying I only want to see index pages for the index that I created with this name, and I only want pages that are allocated. This is being run in detailed mode. So if this was run against a large index, it could take a really long time, but it's not that big, right? It's 2 megs. So looking at this, I can see, once again, I'm getting that this information matches what I saw in the sys.dmdb index physical stats view. I've ordered these results by, and this is an anti-pattern what I did here. So I'm officially ashamed that I have ordered by column numeral. So I'm ordering first by the file ID, then by the page level descending. I should, instead of using the column ordinal there, Microsoft even says you shouldn't do that. I should have put the column name there. So I apologize for my T-SQL sins. They are plentiful. For page level, my highest page level, just like we saw in the physical stats dynamic view, my highest page level is number 2. These are 0 indexed. The leaf is always 0, so that is the 3rd level. Then I have 2 intermediate pages. And the cool thing here is that I can get all their page numbers. And what I'm going to do with this information is I'm going to copy this page number for the root page here. And I'm going to paste it into a command we're going to run, dbcc page, also technically undocumented, but it's well known. It's been around for a while. And so we're going to look at this root page. And I'm also going to copy out the page numbers for those intermediate pages as well, so that we can look through the tree of this. We'll be able to see those child pages on the root page too. We can even tell from this view, this is the page at page level 2. There are no other pages here. It doesn't link to anyone before it or after it. It is alone at this level. At page level 1, we have 2 pages. This page links to this page, which is the next page. They don't have to be contiguous. This page knows that this page is the previous page, so they know about each other. Then at the leaf level, the leaf index level 0 starts here. This is the first level in the leaf. There's no previous page. It knows about the next page and so on. So at each level, there are forward and backward links between the pages. So it knows, oh, the data continues this way, or the previous data was back there. And that, if we think about how a scan works, if I'm going to scan the leaf of the index, oh, all the pages know who the page before was and the page after was. Suppose the page doesn't know, SQL Server knows, but I like to treat these things as if they have brains. I like to anthropomorphize them. It's my favorite word this week. Let's dig into the root page. For certain types of DBCC page commands, you have to turn on a trace flag to see the results, but the type of command I'm running for DBCC page, I'm plugging in an index page and I am telling it I want to return information with what's called dump style 3. That will return a table, and I don't have to turn any trace flags on to get that returned to my session. These are all in data file number 1. That information about what data file they were in was actually returned in the first column on the database page allocations there. So if you ever want to know, hey, what column is this in undocumented, or what data file is this in, the undocumented commands can tell you that. Let's look at the root of our index. The very root of our index knows, it doesn't know the identifiers for all of the pages in the leaf. If we look at what's on this root page, this is the page ID of the root page. That's what we're just looking at. It has 2 rows on it. It knows it's at index level 2, and we have two child pages here and we have their page numbers. We also have these columns that are from the key of the index. It knows it has information for last name, first name, and employee key. These are not the only columns in our index. Let's scroll back up. I'm going to bring the results here. I'm going to go back to the beginning of our script using the little drop down here and say, let's go back to where we started and look at our create index command. The index we created does have included columns in it. The key columns, here it is, the key columns, last name, first name, and employee key, they are all here, but middle name, emergency contact name, and status, there is no sign of them here. The root page in our index does not have the included columns on them at all. And they would take up space. The root page knows the path to the intermediate pages, and it knows one value for one row that's in the intermediate pages. This first page here, it doesn't have any values for it all. These are just null. Now we'll look at that page. The row itself does not have null values there. It doesn't have to track these values because it knows all of the information before this sample value, we're ordering first by last name key, and then by first name key, and then by employee key. So all of the last names that are alphabetically before this last name, they are going to be covered by this previous page. If I want anything before this value, I go here. Anything this value and later, I go here. So it's just a little map based on these guideposts of sample data. Well, let's look at the child pages. These values I already copied out of the previous query, but let's make sure that I copied the right ones. And I need to scroll back to where I am. Let's see here. So we've looked at the root page already. Child page, the first intermediate page is this 158248 that matches what the root page knows. The second one we're going to look at is 158416. So that what we saw in the page allocations DMV matches what we're seeing on the root page. I mean, that's good, right? We want that to match. Looking at this first intermediate page, this is the page ID that we looked at, 158248. We have 186 rows on this page. It knows about, this is just intermediate, so it knows about 186 pages in the leaf of the index. We are at level 1, and the children, we also know what data file the child page is in, so that we can get to the child page by its ID and its file number. We have guideposts for what data is on those child pages too. And notice that once again, in the intermediate level of the index, we have no sign of middle name and the other included columns. We only have the key columns, and they remain in the order that we specified, of course. So last name is our primary sort column. After last name, if two rows have the same last name, then the first name is the next sort. And then finally, employee key. Child page, again, we also have a null value because everything before Abras, Luca is going to be on 158208. So this is our first of two intermediate pages. This is the one who shows up on the root page as the row that has the null values. The second intermediate page, which we're about to look at, it says the data on this intermediate page starts with Surya Sagittaricool. I'm not sure if I can pronounce that right, but I love this name. I am a total name nerd. So Surya, if we go and look at this child page, we would expect for the first data on this page to be for Surya Sagittaricool. Looking at this page, I already have the page ID pasted in here. Sure enough, there are 58 rows on this child page. Notice that it didn't, on these intermediate pages, we have two intermediate pages, it didn't feel that it had to perfectly balance them out. We had 180 something rows on the first of two intermediate pages. This one knows about 58 child pages. We have not, done anything totally weird to this index. We just created it. So it's not always trying to keep the number of rows on the intermediate pages in balance or anything like that. we can see that her data itself, this is not the data itself, this is the intermediate page, because we don't have the included columns here. It's just saying if you want to find the data itself at this value or later, go to child page 158409. That will be in the leaf of the index. Well, let's look at a leaf column, at that leaf page. I'm going to plug in 158409 here. That is the page of the index, a leaf page of the index. And sure enough, there is only one row on it because I specified only 1% fill factor. I said, leave it as really empty. So it just put one row on this page for Surya Sagittaricool. I feel like every time I practice, I get a little better at this name, which I'm probably still mulling, but it's really fun to say. So there she is on the leaf of the index. This is the data itself. And in the leaf of the index, not only do we have the key columns, who we've seen the key columns in the root page and the intermediate page, but we also have the included columns. This is the only place in the index that we've seen them. If we want to find out what the emergency contact name is, it literally isn't any place else. And with these columns not being key columns, with them being included columns, they don't impact the sort order either. SQL Server doesn't order by these included columns. They ride along in the leaf of the index so we can access them. We could check every row and run a filter on them, but it isn't ordering by them. So we've got key columns in the leaf, we've got included columns, and for this page, we only have one row on it. What if I move this row? Let's look at our row right now on the leaf. And this is an interesting one too, because remember that this row, information about this row has been present at the root page and on one of the intermediate pages in the index. This is a guidepost that says values of this and later are this way. What if I change the data in the guidepost? I'm going to change the last name from Sagittaricool to AAA-Sagittaricool. We are going to a hyphenated last name, assuming that this person has decided to change their name. This is going to physically move them in the index because the index is physically ordered primarily by the last name. So this row will move from this page over to the first page in the leaf. It'll now have a different parent too, right? This is currently pointed to by the second intermediate page. So we're going to move it to a place where it actually, if we're going to seek to it, we go from root to the first intermediate page and then to a whole nother part of the index. Her employee key is 38, so that's what's in my predicate as I'm saying update her last name. Well, let's look at the page again. We just looked at 158409. And sure enough, if we look at 158409 again, she's not there anymore. Well, this page is empty. Like, why are we still seeing this key information and included information on this page? Like, is SQL Server just going to leave this page there? Well, let's go up the tree a little bit. Let's go back up to the second intermediate page that says, here are my child pages. Now, this looks weird at first because the first page on here is for the name that we changed. There is now not a row that has the last name Sagittaricool anymore. It is now AAA-Sagittaricool. So it kind of looks like, oh, this information's wrong now. It's not wrong. Look at the child page ID. The page that this data used to be on, the page that's now empty, is 158409. When we moved data off that page and the page became empty, SQL Server went to the intermediate page and it was like, oh yeah, we don't need to go to 409 anymore. There is nothing at 409. And it said, okay, now for this intermediate page, the first child page is 158410. So go there. When we emptied that page, it doesn't want to read empty pages. It doesn't want to use them, but it also wants to minimize the overhead of the change we made. Does it actually have to update the last name and first name at the intermediate page to make seeks valid anymore? No, it actually doesn't, because the rule of data that is this value or higher, right? We're sorting by last name. This guidepost that says go here alphabetically for this row or higher, that remains true. It's just that we no longer have a row that has that exact value. That's actually fine, because these pages, the root page and the intermediate pages, they are like, if we have, if you have a really thick binder full of pages, you'll put little tabs on them so that you can quickly go to a certain part of the data. If I have a huge binder of alphabetized pages, I might have a tab with the A's, with the B's, with the C's, and so on. These are just like those tabs in the binder. I might have a binder tab for X, and I might not have any pages in X at all. That's okay. It's just telling me if you're going for the value of X or higher, go to that tab. And then behind it, there's more tabs. So at the key information in the upper levels of our index are really just so that we can get to the data in the leaf. The important stuff is in the leaf. We don't have to keep this data in the intermediate page accurate for what data exists. We just have to keep it accurate for, if you're looking for data that starts with this value, go this way. It is a roadmap. Well, let's make sure that our data actually does exist somewhere after we updated. We updated the name to start with AAA. That means that if I go back to the first intermediate page of 2, that has a guidepost to all of the last names that are before Abras. If our last name starts with AAA, it should be on this child page, which just has nulls because it doesn't have to record a direction sign for that. It's just everything that's before Abras Luca. So if there was an Abras Adam, it would be on the page before it. So we're going to go to child page 158208, and that is going to be a page in the leaf of the index. So let me put the ID here. This is the A's we're going to look at here. And this page, sure enough, our data was updated, right? It didn't have to be updated in the intermediate level of the index, but it did, of course, have to move in the leaf of the index. So here is the row that we were looking for. She has actually moved, and she's before Abercrombie Kim now. Logically, she is the first row on the page. So I think this is really fascinating in that I think it's very smart that SQL Server figures out how to make the minimum amount of work out of the update. It did have to update that page number in order to move the row on the leaf of the index because it got rid of the empty page, but it didn't have to update the name data itself. What if I update an included column? Let's look at, let's keep looking at Surya actually. So Surya is employee key 38. So what we're going to do for employee key 38 is we are going to add arbitrary middle name because she does not have a middle name right now. We are going to go ahead and update middle name to arbitrary middle name. Now remember, these columns with middle name, this is an included column. It appears only in the leaf of the index. If I go back and I look at this page that has her on it, now the middle name is updated. Now, even though middle name is not going to determine page order, there can be impacts from updating middle name. This was null before. By adding the middle name, this is a variable length field. I expanded the length of the field because this isn't a fixed width field. If this page was full, now it is very far from full. If I had created this index with, 100% fill factor and the page was actually 100% full, it kind of depends how much fits on it. It is possible that after I update the middle name, it is possible the data won't fit on the page anymore. And that SQL Server might do something like a page split to allocate another page and fit the data in there. So by changing included column values, if I do make them longer, I could, depending on how full my page is, cause a physical structure to happen to the index and some rows could be moved to another page. But since I have made my index very, very empty, I am not at risk of that happening. Let's go ahead and change our fill factor on our index. So we are still going to leave it with what I would call a low fill factor. And for an index of this size, I mean, I would use 100% fill. I generally do not fear page splits. If I am in a situation where I am concerned about insert speed and I have gathered evidence to show that I should limit the amount of page splits that are happening, I personally will just lower fill factor by 5% at a time and see how fragmented it gets. So I would, if I'm in a lower fill factor, I would personally start at 95%. I am going with 80% here just as part of the demo to see how does the index structure change if I say you can put 79% more data on a page, because before we had the tree was 3 levels deep. We had a root page, 2 intermediate pages, and then a large leaf. Now, after I rebuild it with 80% fill factor, we're going to rerun the sys.dm index physical stats dynamic management view. And sure enough, our index is much more compact. We only have 2 levels of the index. The level 0 is always the leaf, but our leaf only has 4 pages in it. Notice that we do show, even though we just rebuilt this index, we do show that it's 25% fragmented. When you're dealing with small amounts of pages, it is very normal after an index rebuild to see that they aren't all allocated in order. It is nothing to worry about. When I was first working with SQL Server, I would look at even some large indexes, the upper levels of the index would show, even after a rebuild, they would show like higher levels of fragmentation. And I would think, why didn't that work? I only generally even look at fragmentation personally if there's more than 2,000 pages at that level of the index. So know that it is normal for it not to put every single page in order, and it typically is not a big deal at all when you're dealing with these small page counts. I have a whole 4 of them here. And then I just have one upper level that is the leaf of the index. My page, I asked for 80% fill factor. It ended up being about 78% full. So I will get close to the fill factor that I asked for. Getting the page number of the root page of that index. We have the 4 pages in the leaf, and this query again is that we are returning to our new friend, DMDB database page allocations. We can see the root page on the index, and now there's just 4 pages that are in the leaf of the index, and they each know about the next page. So this is all the same concepts. It's just showing that when we rebuild the index and let SQL Server put more data on the leaf pages, it needs a smaller structure. Now, what this means also, by the way, is the more included columns are only on these leaf pages of the index, right? If we add more included columns to an index, even if we're letting SQL Server fill up the pages as much as possible, even if we're using 100% fill, the more data, the bigger we make that leaf of the index, the more likely we are going to need intermediate levels of the index because we have more pages for it to map to and for it to find. So the size of the data on the leaf or the amount we allow it to fill on the leaf, both of these factors will influence how many levels of the index are required. We now only have 2 levels of the index. Let's look at now the root page of the index, which is at this point just level 1 because we only need the 2 roots, and it knows about the child pages. It has picked out different pieces of guideposts, right? When we rebuilt the index, it rebuilt all levels of the index. It didn't keep the data from the previous root page. It's giving us a glorious new index, and the root page, based on what it saw on, here is where the data on the second child page starts. Everything before that is on the first page. It assigned these new guideposts. These are still guideposts. If I go in and change Chavda and move it on the leaf level, it doesn't necessarily have to go update it on the root page. It's going to be smart about that. We can grab the child page IDs, and let's just see how many rows are on these pages. Grab our 44, 45, 44. There we go. And I think I missed, I missed the first child page. I was like, I did something wrong in my copy paste here. The page numbers may change as you do the demos different times. That's why I don't have all the page numbers in here. So looking at the leaf of the index, the first page in the leaf, hey, it's our old friend, Surya. She's right there with her arbitrary middle name that we've given her, and there are 76 rows on this page. The next page, we should see the first row on the page be Anchor Chavda. Sure enough, that is the guidepost that we saw. It is alphabetically the first the first row on this page, and so on. So I think it's just really cool to get a feel for the index structure by actually looking at, hey, what is the data in these index pages? And I think it's awesome that SQL Server lets us look at the data itself. And as we play around with the data in a test environment, we can really see what's going on in there. So switching back to the slides and doing a quick recap of the biggest takeaways. So we looked at a lot of detail there. What are the biggest things to remember? Our root and intermediate pages, they have information on them about the key columns, but they have information on them about the key columns only. They use this as guideposts to say, if I am going to find, if I'm going to find a certain piece of data, what direction do I go? But like the tabs in a binder, they don't promise that the data from the guidepost is there in its exact form. It is simply being used to quickly go check, do I have data there? This is an example of the page at level 1. So this is an example of, in our demo, the root page after I had rebuilt the index so it was small. We know about first child page, and then if we're looking for rows of these key values and later, we go to this child page. So this is just an example of that roadmap. Note that the data isn't the exact same from the demo. It's not going to necessarily be the same guideposts all the time that you run the demo. It will, as it's building the index, depending on whether it's using parallelism or whether it's not using parallelism, lots of little factors, it may pick different guideposts when it builds the index. Leaf pages have not only those key columns on them, but the leaf of the index is also where the included columns are. The leaf of the index is the data itself. It's where we want to go to resolve the answer for our query. And this is a simplified diagram. I'm not showing all the rows on here. It knows the logical ordering of the rows. It knows the key values and the data is ordered by those. That will determine the row number. And it also has those included columns on it. All of this together means that we can explore the index in different ways. We can seek to data. So we can say, I'm looking for data where the last name starts with D. If the last name starts with D, it is after C, it is before G. So I need to seek down to this child page to get the data. We can also scan the index and use that data in different ways as well. Because we can scan because of these links that we saw where we all know about the next page. If I know who the next page is, I can go down to the beginning of the leaf and scan through it. I could also go to this end and scan backwards. Now, implementation-wise, there are different rules of what I can do. I can't always use parallelism when I'm doing a backward scan in a certain part of the plan. So we may or may not implementation-wise have the same power scanning either direction, but we do have the ability to do it. There's a question about the significance of the key hash value column in the dbcc page command. So this isn't, let me pop that questions tab out again. This isn't on this slide, but if we go back here, there is a hash of the keys. I mean, what this is named is key hash values. So SQL Server is showing us a hash of these keys here. Actually, it's not coming to mind. I'm not sure if, in terms of how that's used, it's not a column that I tend to look at here. We also have information about the row size there. My belief about that column, this is totally made up information, but So my theory that I do not recall if I've ever checked this out, is that probably that could be used to quickly find a row, but that there would be, like when we hash values, when we feed a value into a formula and generate a simplified hash for it, we do have to worry about what are called hash collisions, because multiple values could hash to the same value. So my theory about this, which I haven't thought to look at this in a long time, is that that hash value could be used to quickly find a row, but that it's specifically always going to check the keys as well because of the risk of hash collisions. Now, that theory is just made up of my basic knowledge of hashing. So treat that as a theory. But yeah, great question. The fact that DBCC page, I mean, it could also just be that DBCC page shows this for some reason and it's not actually used on the back end, right? So I couldn't swear to that. All right, so we can seek with this. And when we describe this as an index tree, the reason that we describe this as an index tree is because we have something called the leaf. I think it is kind of confusing to describe it as a tree because when we generally draw the index, we draw the leaf at the bottom of the index. So it's really kind of like, in most of our drawings, this is an upside down tree. So when I actually look at and picture an index, I do personally picture it as an upside down tree. When we look at information about indexes, the leaf is always level 0. This can just be useful to know when you're looking at the dynamic management views in SQL Server that the leaf will always be level 0. So the level that you see of the root page of the index, it will just vary depending on the depth of the index. In this index on the slide, we have level 0 and we have level 1. In other indexes, the root page of the index might be level 4, depending on how many sets of intermediate pages that it needs. Seeks and scans. We're going to use some pseudocode in these slides just to keep it short. Let's say we're running this query. Select the employee key from dim employee where the last name is G and the first name is A. Well, in this case, we go to the root page of the index and we see if the last name is G and the first name is A, rows with the last name G and the first name M start on 158521. So we need to go to the page before that because we're looking for G and A. We need to go to 158520. We will then seek down to that page and see, is there data that fits this? And, you know, I have definitely pseudocode here, and I have even simplified the names of the column in the table. So just imagine that the column name is last instead of last name. So this index structure makes it really easy to seek to data. What if we're running a different query? We want to select the last name where the first name equals A. Well, this index is not perfect for that. We now have a predicate on first equals A. If we are going to use this index, we do have both of these columns. We can use this index because we have the last column and we have the first column, but all of our data is sorted initially by last. So the data with the first name A, it could cause me to spill my coffee. It could be anywhere in this index. I get so excited about indexing that just things start flying around. It does make these things kind of expensive sometimes. So if I did have another index that was keyed on first name, that might be attractive to SQL Server, especially if that index also had the last name column somewhere in it, maybe as an include, maybe as a key. But assuming I don't have that, SQL Server could possibly make the choice of like, well, this index isn't perfect for me, but I do have the ability to say, okay, this data where first name equals A, it could be anywhere in the index, because we're ordered first by last name, but I can go to one end of the index and then I can go to the next page and the next page and the next page. And while I'm looking at this index, I can apply a filter. I can check every single row and say, is your first name A? Is your first name A? How about you? Is your first name A? And then just return the rows that I find. And this will show up in an execution plan as a predicate. If we are seeking on a column, it will show up as a seek predicate. But if we are just checking every row and filtering out for a value, then it will just show up as a plain old predicate. So this index will work for this query. We will have to read more pages from it though. And this will show up as a scan of the index in this case. Well, okay, what if I'm doing something similar, but I am querying an included column? And imagine that I have an included column that is actually named include in this case, just for brevity for fitting things on the slide. I have an included column whose actual name is include. Now this time I'm putting the predicate on the included column. Before I was putting it on first name, which at least is in the key and it's on the root page. SQL Server can still use the index. Even though the root page of the index does not have any included columns on it, in the metadata, SQL Server knows what columns are included in this index. And SQL Server could say, all right, I'm looking for a specific value for include. Now, if I had another index that had this column who's named include, if it was the first key column in that index, maybe I'd go use that. But assume we don't. Assume we just have the base table itself and this non-clustered index. SQL Server may choose to use this non-clustered index for this query because it can say, okay, you want to know where include equals z, and that isn't anywhere in my root page, and it's not going to be in my intermediate pages if I have that level either, but I can go to one end of the index, I can scan, I can look, just like when we were looking for the second key column as our only predicate, I can check every row and I can filter it out. So it knows that we can find all the pages and check for this data, even if we're putting a predicate on an included column. This will also show up as a scan, but it's actually really cool that it can do this because this non-clustered index may have many fewer pages than the clustered index of the table itself. SQL Server is smart enough to say, if there isn't a perfect index, if I'm gonna have to scan something, I'd like to scan the thing with the fewest pages because it's less work to do it. So this index kind of covers this query. And I say covers in the sense of SQL Server could get the answer from our query from this index without having to go to the base table itself. All of the data it needs in here is in here, even though it can't seek to that data, even though it's not, this index is not optimized for this sample query. And this is very, very good because it means that if I designed this index to be really useful for a query that cares about last name and first name and employee key, this index can still also be pretty useful for other queries who aren't tailored to it exactly. All right, so we got a 3-question quiz. So bring up your Q&A panel so that you can vote. Your answers are anonymous. I will not reveal your identities in your answers. So question 1, for this query, we are selecting employee key from dim employee where last equals C and first equals G. That data in this case looks like it's actually in the root page of the index. Does SQL Server actually have to read the leaf page of the index, yes or no? And by the way, you can prove this and trace what buffers it actually reads from. We've got 1 vote for yes. We've got 1 vote for no. Is anyone willing to be the tiebreaker? We've got 1 vote for yes. We've got another vote for yes. So the yeses are leading that it needs to read from the page. Let's see here. We've got another vote for yes there. This does seem like when we look at this, it does seem like, hey, the data that we need is in the upper level page. But remember how when we could update values in the leaf and it doesn't have to go update the values in the intermediate level of the page. SQL Server does have to go to the leaf because that row of CG, it actually could have changed and moved. It's simply that the little guidepost of data that's alphabetically here or higher still remains. Also, even if that data hasn't changed, how many rows are there where last equals C and first equals G? This guidepost at the upper level of the index, it says data starting with this value is on the page, but it doesn't have any information about how many rows there might be with that value. We could have 2 employees or 3 employees whose last name is C and first name is G. It has to go to the leaf to actually find them. So the data is in the leaf is the way that I remember. The data that we're looking for is in the leaf. All the upper levels are just ways that we can find the data. So the data itself is in the leaf. Question 2. we are going to update a row. And this, I have changed the schema of the table slightly. Imagine that our data was like this, and we do have 2 rows for employee. We have 2 Alice Chapmans. There are 2 of them, or no, actually, I'm sorry, I'm goofing. There is one of them. The table is different, and I'm explaining it wrong. There's one of them because they have the same employee key. But this is a table that has contact information for them. Alice has 2 emergency contacts. One of them is ID 1 and one of them is ID 2. We are changing the emergency field where employee key equals 38 and contact ID equals 1, and we are setting that to Zelda. So it's going to change from Jackie Chen to Zelda. Is that going to change the row order on this? Votes are coming in, and I have to make sure I understand whether the votes are for question 1 or question 2. I think all our votes are for question 2 are for no. I should have been like, put the question number in your vote, but everyone, yeah, so we've got to vote Q2, no. That is correct, even though, and in fact, even if the contact ID key wasn't in here and they were equal, this is not going to change the row order if we update an included column. And we know it's an included column because it doesn't say key on it. If the page is full and we were to make the value longer, we could cause some pages to change if there wasn't room for it. But in fact, in this case, we're making it shorter. So making it shorter shouldn't have that issue. So that is the row for Zelda. So included columns aren't sorted, which can be useful. So final question. And so for this one, let me scroll down to the end of the question. So, okay, I know where, an alleged DBA, I love your sign-in name. I can reveal your name because I suspect your name is not actually alleged DBA. You have the final vote for Q2. So for Q3, we did not cover this one, but are seeks good and scans bad? This is one of the things when we talk about indexes that we hear earliest on, is that when you tune a query, you want to look for seeks and we want to design seeks. So, and this is an opinion question. We've got an it depends. We've got another it depends. We've got a third it depends. Well, what does it depend on? If you say it depends, I think you kind of have to say what it depends on, because when I answer the question, I kind of have to do that too. We've got a no. We've got a yes and no. We've got a seeks are good. Now, I like that answer because that answer says seeks are good, but it doesn't say that scans are bad. So this is citing on, I actually think that's a very clever answer, that seeks are good when we've got a no there. So let's talk about this. It's tricky. We didn't show a case of this, but the thing about a seek operator, seeks are usually good, is maybe, I would maybe hedge even more than that. Seeks are good if they're good enough for our use, all right, depending on what performance we require. The thing about a seek operator is, so imagine that everybody in my database has the same last name, because what my database is actually a genealogy database for my family, and it's actually all the littles. My table for people that I'm seeking on, the last name for everyone is actually little, because it is a table full of littles. If I put an index on last name on that table, my first key in the column is last name, I could say, okay, I want to find all the rows where last name equals little, and it could technically be a seek, but it's every row in the table. Just because it's a seek doesn't actually mean it's going to narrow down the rows. And this can be really tricky when you're looking at execution plans, because you're just glancing at operators and you see a seek and you're like, oh, it's seeking, it's good. But then you hover over the operator and you see that you're seeking on a column, and then above it, there's either no other predicates and it's a non-selective column, or there's a ton of predicates listed without the word seek in front of it. So it's actually checking tons of rows in the table and filtering it out, because whatever the keys are in the index, there's one key it can seek on, but it's not very useful. So we do have to check with our seek operators, how many rows are you reading? How many rows are you filtering out? Is this seek very selective? Is the question that I would ask. So a seek may be great if it's really selective. If it's not very selective, it may not be any better than a scan. Similarly, scans There are cases where a scan may only scan part of the index. If you're doing a top operator, for instance, it may scan a little and then stop as soon as it gets, if you've got a top order by, as soon as it gets the data it needs, it can stop scanning. So generally speaking, you have to look at how selective are they, how selective should they be. So it depends on how efficient they are in each case. And scans can actually be awesome. If we do want to scan all the data, a scan can absolutely be awesome. All right, well, we have reached the end time just on time. I slid to the questions slide just in case. And since folks were asking questions during the webcast, I think we're pretty good because I think I got to them. Oh, and we did get some answers to the last one. Depends on the size of the scan. For bigger tables, scans can be good. Yeah, if we need to aggregate all the information in a column, a scan can be great. And maybe a column store index might be great for it too. Seeks are good and scans are sometimes okay was an answer. Yeah, seeks sometimes can be even better seeks. Depends on the table structure. Scanning of a small table is okay and maybe faster. Yeah, if I'm sometimes scanning a table that's 4 pages, how much of a difference is it going to make if it's happening sometimes? And we have a question as to whether Little Bobby Tables is in the table of littles. I consider Little Bobby Tables to be a family member. I totally do. Little Bobby Tables and me, we are definitely buddies. Well, all right, folks, thank you so much for joining me today to nerd out on indexes and have fun. If you want to play with the code there at this URL, there is also some links to free online quizzes that I've got on the site if you want to play around with it. And I hope to see you guys around the webinar universe soon. Thanks so much for being a part of this virtual chapter. And yeah, have a great week. I believe it's Wednesday. I've started working on Saturdays sometimes now, and it's a lot of fun actually. And so figuring out what day of the week it is becomes complicated. So thank you, Kenny, for being our host. And I am going to go ahead and close up the webcast.
All right. Thank you very much, Kendra. See you all next week.
Bye.
Bye-bye.